Hello and welcome to Learning Image Analysis. As before, my name is still Lawrence Small, Application Specialist here at MIPAR Image Analysis, and this is Lesson 3 of Section 1. We're talking today about the anatomy of an image. By the anatomy of an image, I mean the data inside of the image, I mean how the image was initially constructed, all that good stuff. So let's set the scene. You have your subject, and you decide that the best way to capture data about it is to image it. So you set your equipment up, you point it at your subject, and you hit the button. Presto, an image comes out. You then find your features in the image and measure them. But there's a problem. If you don't understand what's going on as the image is made, your data might not even get captured. There may be nothing to measure, or even worse, you may be measuring features that have been distorted, and you then get incorrect data. So the goal for today is to understand the data in the image and how it relates to the subject that you initially tried to capture. So we'll talk about the data stored in the image file, the actual numbers and bits and such. You'll also learn about image formats and how to choose the best one for your particular application. And along the way, we'll talk about different acquisition errors and analysis errors that we see and how to avoid them. So, how an image is made. You start, of course, with your sample right here, and you illuminate your sample with the imaging beam. This beam could be made of photons, light. It could also be made of electrons, sometimes even sound waves. But whatever you're using, the beam hits the sample and reflects off, and then there's some sort of focusing apparatus that focuses that beam onto a detector. Now this detector is made up of a whole bunch of little detectors, each of these tiny squares. And this little detector will read how much illumination it is getting hit with. How strong is this beam right at this point? And then that level, that strength, gets converted to the value in a pixel in your final image. So your computer actually stores these values as numbers. So for in this case, pure white is the number 7 and pure black is the number 0. So the computer itself can only deal in zeros and ones. If you know, a digital computer deals with binary numbers. So the 000 is 1 and the 111 is 7. So this would be a 3-bit image because there's 3 bits here. Now in real life, most images are 8-bit, which means it can go from 0 all the way up to 255. The important point though is that you can't go below 0 and you can't go above the maximum of your image. So whatever level in the detector that you set as 0 and whatever level in here that you set as 255, anything above that or below that gets clipped off. Let me show you this interactively. Here we have some cells that were illuminated using fluorescence microscopy. And what we have here is a demonstration of what will happen to the image if you adjust the power, the exposure, and the gain in your microscope to set the levels of 0 and 255. So I'm using, technically it's an adjust contrast on the after image, but the concept is the same. So we have, in these cells for instance, here's several features all together, and if you crank up the gain or crank up the exposure or the power of your imaging beam, you increase the value of those numbers, the amount of light that's hitting the detector, and you can completely blow out your features, which is bad. No longer is that information all in the image. All that's lost forever. And you can do a similar thing to the background here. So as we turn up the gain or turn down the gain or the exposure or the power, you lose the ability to see that background. Now this might seem like a good thing, but it's really not, because this background here contains valuable information. It contains information about the noise that's in the image, and if you make the wrong choice, you could end up accidentally cutting off the sizes of your features. Maybe you can artificially make them look smaller than they are. Or you could lose dim features. And all this adjustment is especially dangerous if your image itself isn't illuminated evenly, if you would need different values of exposure in different parts of the image. So it's important to have your levels set so that you capture the background and you don't blow out any of your detail. Okay, so if we have the entire image caught like this, there's no zeros and there's no 255s here on the screen, so we have all the information that's possible to collect in this image. So our takeaway here is that if you're not careful with your microscope settings, you can produce a misleading image by blowing out detail or potential information on noise that you would need in your image. And I encourage you, don't over or underexpose your images. Don't clip the data off above or below the limits of your color scale. So now let's talk about spatial information in your image. We saw earlier how the detector is made of a bunch of little detectors, and each little detector turns into a single pixel in the image. So if we zoom in really far on our image, here we can see all the individual squares, all the individual pixels. Now, the fact that the image is divided into pixels rather than being a smooth, continuous representation of your sample means that necessarily some information is lost. This is known as the resolution of the image, how small those pixels are, and technically the distance between two features that you can distinguish based on the pixel size. So of course you can't reliably measure the size of features smaller than a few pixels. So is this feature here a pixel, half a pixel, just over a pixel? You can't really tell. And you can't distinguish between two features, of course, without an empty pixel between them. Right? Is this two features or one? Again, nobody knows. And lastly, pixels that cover the edge of a feature become faded, because only half of the detector will then get illuminated with that piece. And so all these gray values that you see here are because of that. So really what you have to do is know the limits of your imaging system. You have to know what the pixel size is. Most microscopes will report that number to you. You have to know, based on that, what distances, what sizes you can measure, what could be reliably accurate in your image. And if you want a certain level of detail in your data, you need to know that ahead of time, and you need to adjust your resolution if possible. One thing to note is that noise in your image can make your effective resolution not reach the theoretical maximum resolution. For instance, take these two supposed features here. Are they really two features? Or are they one feature that was cut by a bit of bright noise? Now it's one pixel across. Nobody really knows. So you can make an educated guess that this is one line here that was cut in the middle because of how they continue like this. But technically that information isn't stored in the pixels itself. You have to make some assumptions in order to come to that conclusion. So now that we've talked about intensity and we've talked about spatial information, let's talk about color in the image. So if you remember from art class, the three primary colors of red, blue, and yellow. When you're talking about light, the yellow gets replaced with green because those are the three colors that your eye can see: red, blue, and green, if you're not colorblind. And so when you want to take a color picture of an image, what the camera does is it actually has three separate detectors, in essence. One that captures red light, one that captures green, and one that captures blue. And these get stored as three overlapping images known as channels. And so this is the data inside the computer, three separate copies of your image, one with each color stored in it. And then when you display it, each of these channels gets run through a color map here, and then they get added together. Red, green, and blue all together equals white. So, multi-channel images are used for storing the three primary colors, captured from a colored subject by three color-specific detectors. And you might find when you go to start analyzing those images that one channel has the information that you want. So for instance, often we see that the green channel is more in focus, while the blue channel is not very in focus. It's known as chromatic aberration. That happens actually quite often. Also, based on the color of features, you might care about one channel over another. If you're trying to find red features or green features, you might use one channel or the other to see those. Now, something to note is that theoretically, you can stick whatever data you want in these channels. It doesn't have to be from three colored detectors. So for example, if you were in the life sciences doing fluorescence microscopy, you could have a red fluorescent protein and a green fluorescent protein. And if you image each separately, you can then store them as two different channels in the same image. So here we have our green fluorescent protein GFP mapped to a green color scale displayed on the image. And then we have our red fluorescent protein, RFP, mapped to a magenta color scale and displayed on the image as well. And then magenta plus green is white. Just as a side note, I use magenta here instead of the typical red because colorblind people can't tell the difference between red and green. So it's starting to become more common in the life sciences to show magenta and green equals white rather than red plus green equals yellow. So, just a pet peeve of mine. I recommend using magenta instead of red. But back to the multi-channel data. Now it's tempting to analyze the displayed image. For instance, if you wanted to find co-localization, if you wanted to find places where your red fluorescent protein and your green fluorescent protein overlapped within the cell, you could look at the displayed image and find all the places that are white. Say, aha, this is where they overlap. But that can be dangerous. So perhaps the two channels don't have the same intensity. Your two proteins aren't expressed to the same level. And so one is dimmer than the other. Then you're not going to see any white. You'll see more either pinkish or greenish. And say, for instance, that there's some texture inside one of these proteins in its distribution that doesn't affect where you consider its localization to be. And that texture could then influence the displayed image. So it's more accurate to find the location of each signal independently in its own channels, and then take that processed data and perform co-localization analysis on that. So you'd circle this and you'd circle this and find where those two circles overlapped in between them. Now, the last point I want to make about color in an image is that sometimes that color is artificially added. So we have our 0 to 7 in this image, and you can take it to a regular grayscale color map to produce your image. Or you could map these numbers to whatever you wanted. Green, blue, purple, all in a row, and then display the image that way. So this is often used for visualization. It's easier sometimes to see red from orange than it is to see two different shades of gray from each other. So that's fine. But it transforms the data, so this turns now into a 3-channel image of red, green, and blue to add together to form all these different colors. And unless you know the way that this single array of numbers was mapped onto a color image, there's no way to go back. You can't just look at this and say, aha, this color was this original intensity. So if you want to try to analyze this displayed image, you will lose a lot of accuracy in your information there. So this is fine for visualization, but do not analyze these color mapped images. Only analyze the raw data. Our next point is image compression, how the data in the image is actually stored on your hard drive. So sometimes image files can get massive. If you have really fine resolution, if you have 3, sometimes more channels depending on the instrument. I've seen images up over 300 megabytes for a single image. It's just giant. So image files can be giant, and data scientists have spent a lot of work to try to figure out how to pack that data into a smaller space. So essentially, this lets these images get sent across the internet faster without taking up a long time for your images to download. That's one of the reasons that image compression is so useful nowadays. And a lot of image formats have been developed specifically with this in mind. GIF, JPEG, PNG, all these different formats are all designed around compression and also the color space that they are able of holding. There are 2 types of image compression, lossless and lossy. Let me give you a quick analogy. Imagine a Ziploc space saver bag. It's a giant bag that you shove your clothes in, and it's got a hole on the side that you hook your vacuum up to. And the vacuum sucks all the air up and compresses your clothes down into a smaller space. That way you can shove them under your bed or pack them up into boxes for the winter. Lossless image compression is like this. Your clothes stay fine. They're all well and good in there. They might get wrinkled, but that can be ironed out. And all the air, all the extra stuff that isn't needed, that's removed. So the image in lossless image compression is unaltered. So examples of this are GIF, PNG, and TIFF compression sometimes. Sometimes TIFF images you might find are uncompressed. Just your clothes in a giant pile. But it can also be compressed the same way that PNG images are. So that's lossless. Now what about lossy compression? This actually throws information away. It can produce a smaller image file than lossless compression, but then information is gone. So going back to our analogy, it's like the vacuum that you hooked up to your space saver bag. Not only did it suck out some air, but it also cut out pieces of your clothes. And now those clothes are they're gone. Those pieces are cut out and thrown away. So information is actually destroyed when you do lossy image compression. Now they try to do their best to save important information while only throwing away unimportant information. But still, by definition, information is lost. So when you analyze a lossy compressed image such as JPEG, you're getting less accurate results. So JPEG itself will break your image up into blocks and then give an approximate description of each block. I'll show an example on the next slide. Essentially, it's a low-pass frequency filter, approximately. If you don't know what that is, we'll talk about that in the next section of the course when we get to Fourier transforms and frequency analysis. But here's an example of PNG versus JPEG compression. We have our cells here, and you can see all the detail in the cell that the lossless image compression preserves. The lossy JPEG compression, we see the blocks that it broke the image up into, and then the approximate description in those blocks, so the lines don't add up properly. A lot of the fine detail within a block is lost. So this is a pretty extreme example of JPEG compression. I think I have 15% quality here, but it demonstrates the point that you don't get a perfect representation out. Now, if you know what you're doing, you can decide what level of accuracy and detail you care about in your image. And you can use a level of JPEG compression that preserves that amount of detail. So you can use a light enough compression that you don't destroy what's important to you. Which, okay, is fine. Great. You get to save a lot of space on your hard drive. But just be aware of what you're doing when you do it. And another note, you can't take this image and save it as a PNG and expect to get that data back. It's gone forever. If you were to convert this image back to a PNG file, you would get a perfect copy of a ruined image. So have fun with that. So some takeaways for this point: if you have the disk space, I very much recommend using PNG or compressed TIFF images. If you need to compress with JPEG, for instance to send it across the internet rapidly, first you need to consider the level of detail needed for your measurements, and then use that to determine the level of compression. And if you have a backup hard drive somewhere, I very much recommend keeping a copy of the original, because once you've compressed an image, you can't go back. Our final point today is when you have a subject that can't be represented appropriately with just a single image. Say your sample has some depth to it, and so you'll need multiple images that slice through your sample. Or maybe you want to capture an image, a subject in motion, and so you need multiple images throughout time. So an extradimensional image stack is a series of images collected to represent changes in space and time. So they're known as Z-stacks if you're collecting a volume, or time series if you're collecting a movie. And once you have your image stacks, you can then analyze the images individually and then recombine the resulting information into a three-dimensional volume. Or you could stack them together and analyze the whole volume at once. You can do the same thing for a time series. You can track particles from one frame to the next, and you might do that by analyzing each image separately or by analyzing the whole time series at once. It just depends on the nature of your particular sample. Now, as with pixelation that we talked about before with spatial information in your image, with Z-stacks and with time series, you need to make sure you're sampling frequently enough to capture the features you want to capture. So you need to make sure that your spatial resolution is tight enough to tell that this is really a sphere rather than a pyramid or a cone or something. And you need to make sure that as particles are moving, you have enough time resolution to be able to track individual particles and not have large jumps that would cause you to confuse one particle with another between different images. So you need to be careful to make sure that you sample often enough. Another issue that comes with extradimensional image stacks is that the different images often need to be taken separately. So you take one slice through your volume, and then another, and then another, and then another. And of course, a sample moving through time, you need to capture one image, then the next, then the next, then the next. And the issue that we have then is that the subject, or the microscope, may move during stack acquisition. And that's going to throw off your volume or your movie rendering. So if possible, eliminate as much movement as you can before you start your acquisition. So do as well as you can beforehand. Then afterwards, sometimes this movement can be corrected by image registration. That's where you look at one image, look at the next, find a feature that you expect to be the same in both, and then use that feature to realign the images. It's not perfect. Sometimes it won't work depending on how much movement you have and whether or not you actually have a reference that you can use, but it's something to try. But a common theme is that as much as you can fix before you take your image, that much better your analysis will be. Another consideration is how you're going to store the image stack. Some file formats can have the entire stack in one file. TIFFs are really good at this. On the other hand, if you're using PNG or something, you might just have 500 image files all in a folder. And so they have to be numbered sequentially, and they have to be processed sequentially as well. So just keep that in mind. Many microscopes, their manufacturers have proprietary formats that can hold this sort of multidimensional image. And also note that not all software can process the entire stack. Some can, some can't. If not, you'll need to split the stack up into individual images and then process each one individually. In conclusion, we've talked about how an image is constructed by the microscope and the detector, and how the intensity of light that reflects off of or is transmitted through a sample is converted to numbers stored inside the computer. And so we've learned that different parameters that you have during image acquisition, like beam intensity, exposure, gain, sensitivity of the detector, all that determines the final 0 to 255 data that's stored inside the image. And you want to be careful not to blow out detail or clip off the background. We've also talked about spatial information, how detection is done in pixels, and as a result, there's a limit on the resolution of spatial information in your image. And make sure that you have enough resolution to measure what you want to measure to the accuracy that you need. We've talked about image compression. We very much recommend using lossless image compression if possible. It's useful and it's harmless. Lossy image compression is irreversible, and you have to be careful not to destroy the data that you need. So of course we recommend using TIFFs and PNGs and reserving JPEGs only for when it's absolutely necessary. Finally, we talked about multidimensional image stacks, Z series going through a volume, or a time series going through time. And if you're going to take an image stack, make sure you have your imaging set up carefully. That way that you don't have to deal as much with image registration and focal drift and things like that. And make sure that you have analysis software that will properly be able to handle the data that you're going to give it. If you're looking for more information about acquiring images, about microscope settings, all that good stuff, I recommend going to the microscope manufacturers' websites. A lot of them have tutorials, lessons, that kind of thing. We'll have a list of websites that you can go to in the description of this lesson. Often the microscope companies will also have application specialists. So if you purchase the scope from them, they'll have people there to help you use it, and they can help you set the proper gain, set the proper exposure, that sort of optimization that you might need to collect the data that you want in your image. If you work at a university, especially a large one, you also might find that there's a core center that specializes in microscopy, and they'll have experts on staff to help you collect images and analyze those images. Lastly, you can always go to ResearchGate and ask a question there. There's lots of people interested in helping, and you get a lot of good information. Next time, we'll talk about the image analysis workflow. So how do you decide what data you actually want to extract from your image? What an image processing algorithm might look like that's designed to extract that particular data, and how you would go about actually developing that algorithm. We'll also touch on how some image analysis concerns can influence your experimental design. Thank you very much for listening. We'll see you next time.